Hello everybody, I'm Matteo Andreottola. I will present myself. I worked for a few years in Ireland as a structural engineer for a timber company. Then I moved back to Italy and I worked a few years for Xlam Dolomiti as a structural engineer again. And currently I'm working as a technical consultant for Rothoblaas. Okay, in the lection of today, we are going to talk about the waterproofing and the airtightness in timber buildings, and in particular, we're going to see how to seal a timber building, how to deal with the durability, and we're going to explain the membranes as well. We are going to talk about why membranes are so important in the design of a timber building, and we are going to see, last but not least, the reaction to fire that our membranes have. So first of all, it is important to talk about the physics. It's very important to know some theory before actually starting to talk through all the membranes and how to choose them. So how does it work? So in the air we have always vapor, and the vapor is trying to escape from the building, because inside usually there is a high pressure. So it is very important to design properly the wall buildup or the roof buildup, so that we don't have structural issues of our timber structure, which especially with a timber structure is very important to avoid, and of course to make sure that the people, the inhabitants of the buildings are living in comfort. So basically, when the vapor is passing through the air and the vapor is passing through the wall, there can be some issues, and these issues can be interstitial condensation, which is a condensation that happens inside the wall, and also superficial condensation, which is the same thing, but it happens on the outside, on the outer surface of the wall. So both of these issues are very bad for our timber structure. So it is very important to understand how to avoid them. So let's have a look first of all at the damages that superficial condensation, for instance, can make on our buildings. So superficial condensation is a problem which affects mostly the visual part of our building, so the finish of our wall, for example, in this case scenario, and the damages caused by interstitial condensations are worst for two main reasons. First of all, because usually they happen. It's condensation which happens inside the wall thickness, and so therefore you cannot see it, so you cannot see the damage. That's why it's very dangerous. And second of all, interstitial condensation is very bad because it can actually affect the structure. So if you have condensation which is happening inside your wall and you have a timber structure, of course you know that timber is very sensitive to water and to vapor, and therefore water and humidity can actually damage severely our structure. This is, for example, an example of what I was previously talking about. For example, in this floor buildup, some designers chose the wrong membranes, and therefore we had condensation on the inside. And as you can see, when they opened up the floor buildup, they saw that all the timber structure inside was completely rotten. So this is a picture to keep in mind when you're designing a timber structure, for example, is a picture that you always have to keep in mind, because the design with membranes, with the right membranes, is very important to make sure the durability of your building works in the right way. So let's see how condensation and how the condensation works in particular. So when we have air, it always contains vapor, of course, and the hotter the air is, the more vapor it can contain. So when we are cooling down the same amount of air as we see in the image here, so we just have the same amount of air with the same amount of vapor inside, and we can see that while we are cooling it down, we are reaching the saturation. And when actually when we reached that saturation point, we have all the water molecules that are contained into the water. They have to escape from it. So to explain this in easier words, we can for instance think about hot air, which is coming in contact with a cold surface, and as we all know, we see all the condensation. So the water drops onto the cold surface, and that's because the water cannot be contained anymore into the air. And so temperature, as we understood now, is very important, and humidity. So these two things are very important to keep in mind. The relationship between temperature and humidity, that's really the two things that you have to talk about. So just to give an example, a family of 4 people is producing approximately 10 kilos of humidity a day, just cooking through our breath, for instance. And so this can actually make a very unhealthy place in which we live in. So the easiest thing to do, most of all, is ventilating the room. Of course, that is not always possible because, for instance, if it's very cold outside, if it's winter time, if you open up the window for too long, you really have some also a loss of the heat that you have inside your building. So another way is use of a hygroscopic material, but that's not always easy. So really, the way how this works is through transpiration. So pretty much our walls and our roofs are continuously breathing. So vapor and air is continuously passing through, really. So again, temperature and humidity are, again, I highlighted it and again because it's the most important thing. So how does it work exactly? I told you that the wall is breathing. So basically we have on the inside a bigger amount of vapor and a higher pressure as well. So this vapor tends to migrate, tends to pass through our wall buildup. And as I told you before, there's another thing to keep in mind. Passing through the wall buildup is gonna encounter zones with different temperature, and we just explained before that when the vapor contained into the air reaches a certain temperature, which is about 13 degrees usually, it can condensate. So we don't want our vapor to condensate on the surface, neither on the surface or on the inside of our wall, for example. So the temperature is very important, as I told you before, and this is a picture done with a thermal camera, and as you can see, the parts of our building, they are not always the same temperature. We have places, for instance, like around the windows, for instance, or when we have cold bridges, we have the temperature that is dropping down into some parts of our structure, and this is very bad because it can cause that condensation, because we always have vapor inside, and if the temperature is dropping down, it can be very dangerous. So it's very important to talk about the thermal conductivity, which is this lambda here that we are seeing. So different materials, They have different thermal conductivities. In timber structure, for instance, we are lucky in a sense because the timber has a very low conductivity, and therefore it helps out the to isolate to the insulation of the structure itself. And so we can see here in the graphic some other construction materials, for example, some very common construction materials, and concrete, for instance, or clay bricks they have a higher thermal conductivity, for example. So let's have a look at how to study the condensation inside a wall buildup. So we study it through this Glaser test method, and that's a way to find the dew point inside a wall construction. So we can see in the graphic two lines. One of them is the vapor content, and the other one is the temperature. And if the two graphics, if the two lines are colliding, like in the first case scenario, we really have an issue of condensation. In this case scenario, we have interstitial condensation. If the two lines are apart, that it's not a problem. So the Glaser test worked, and we're sure, let's say, that condensation is not happening inside our wall. Another very important thing about material is the SD, and the SD is an indicator of the resistance that a certain material is offering to the passage of the vapor. So we're gonna see again the SD when we talk about membranes, because it's very important to study the SD when you're choosing the right membrane. So it's measured. The SD is measured in meters because is the thickness it's the thickness of an equivalent layer of air which offer the same resistance to the passage of vapor as that of the material. So that's why it's in meters. And so inside our wall thickness, it is very important to have vapor control layers on the inside, and it's very important at the same time to have materials with very low thermal conductivity on the outside. So insulation material on the outside, so that our wall remains warm and there isn't too much vapor passing through. And if we try to keep these two things together, we are sure that we won't have condensation. But what do we do in the case that when, for instance, we have a buildup which is in this situation? So when we study it and we see that there might be some interstitial condensation. So we are going to use membranes, of course. So all the membranes are water. They have water tightness. So that's a common characteristic of all the membranes. And another characteristic that all the membranes have is the wind tightness. So all of them can be used for the wind tightness and air tightness as well. What changes is what we just explained. So the SD, so the resistance to the vapor passage inside through the membrane. There is another main difference in membranes, and it is the following. So we have membranes which are monolithic and other membranes which are microporous. What is the difference? The monolithic membranes are the vapor can pass through with a chemical reaction. So as you can see in the image, all the molecules are in contact with each other. So it's a unique layer. Let's say like that. In the microporous products, all the molecules are produced in a way that there are some very, very small gaps between a molecule and the other. They're not holes, of course, because they are still waterproof, so we don't have holes, but the water molecules, the vapor can pass through through capillarity, you know, throughout these small gaps that are formed. And another thing to keep in mind is the water tightness, of course. And I want to spend 2 words on this. I told you before that all the membranes are they offer as a feature water tightness, and that's of course a very important feature because we have to protect our building and our structure from the water. But they are not meant to withstand the steel water. So let's give an example. For instance, when you have a balcony and there is it's raining on top of it. First of all, you have to design the balcony in the proper way. So you have to design an slightly inclined surface of the balcony so that the water can escape very quickly from the structure itself. Of course, you have to place as well a membrane which is protecting our structure from this running water. So let's explain what water column is. It's a test that is done onto all the membranes, and it's basically a column of water is placed on top of a membrane. Of course, it doesn't have a bottom cover, so water can pass through, and it is measured the time which the membrane can resist, preventing the water to pass through. Now, to keep the level of attention higher, we are gonna show you a very short video about the water column, so that you can see the resistance to the water passage that a membrane can offer. Another very important thing when you're choosing the right membranes, because there are, of course, a lot of membranes out there, and it's very important to choose the right one. So another very important thing is the tensile strength. And I'll give you another example. For instance, when you're onto an inclined pitch of a roof, and the installer, for instance, is stepping onto the membrane with his feet, and there are maybe some nails to keep the membrane in place. It's a possibility that you have is that the membrane tends to tear apart. So, for example, when you're placing a membrane onto an inclined roof pitch, it's important to choose a membrane that is that has a good resistance to a very good tensile resistance. And for example, to prevent the tearing. Another very important thing is the UV stability, and of course a lot of membranes are inside the build-up of the wall, the construction of the wall. But when you're on site, of course, and you leave maybe the membrane to protect your timber building, sometimes the on-site works can stop for months, sometimes even more. So you have to make sure that you prevent this. So you don't leave your membrane for too long outside, And low temperature can be a problem, but is less of a problem, really. So let's have a look of what kinds of membranes we have. For example, let's start from the vapor barrier. So that's as you can see below, it's a barrier that stops completely the vapor to pass through. So let's see where we have to place it into the build-up, and I will show you immediately. So that's where you have to place it. So on the warmth side of the construction, of course, because you need to prevent the vapor from getting into the your floor or your wall or your roof, for instance. And another kind of membrane that you can place in the same place, so on the inside, on the warm side of your wall, is, for example, a vapor control layer. So it's similar to the previous one, but it's a membrane that lets some of the vapor pass through and stops some other part of it. So it's actually controlling the passage of vapor that we have into our wall, for instance, and it's placed exactly in the same place, so in the warm side. And I want to explain something better. So you would say, why choosing this vapor control layer when you have another membrane that can stop completely the vapor from getting in? So that's a very good question. And the thing is that when you're placing a vapor stop layer, so a barrier, you have to make sure that you don't leave any gaps, because if you have a gap, all the vapor will all converge there. All the vapor will try to pass through that single hole, and that can result in a local damage. And on the other hand, when you have a vapor control layer, the vapor is passing through all the surface in a controlled way, of course, but it's passing through the whole surface of the membrane, and therefore, even if you have a small gap, it's not such a big issue. Of course, it's always better not to have it. That's for sure. So choosing a vapor stop layer is better when you have people inside, which you are 100% sure they are gonna do a good job. And on the outside of the wall, of course, you have to prevent water to get in. You have to make sure that also the wind is not getting in, because if the wind gets in, the temperature of the insulation layer, for instance, is dropping down, and we explained before that if you have low temperature and the same amount of humidity, the condensation risks increases because it's easier to reach the dew point. So on the outside of your wall buildup, you can place the breathable membrane. So once the vapor passed through the vapor control layers, for instance, it has to escape out, to get out from your wall as soon as possible. And so the breathable membrane is a membrane that is, of course, that lets the vapor go through, but it stops the water from getting in on the other way. So as we can see in this image, is placed on the outside of the roof or wall. And in a technical sheet, for instance, in the one that I'm showing to you right now, you can see all these characteristics that our membranes have, for instance. So it's very important to study in the right way the technical sheets. And for instance, here you can see the vapor transmission, or and also all the other characteristics that we just explained before. So that's just an example of how a roof build-up would have to look like. So you can see that on the inside, on the warm side of our insulation, we have our vapor control layer. We have, of course, the insulation, which is very important. And on the outside, we have a breathable membrane. And it's important as well to have ventilation, if possible. And then, of course, the finishing layer, or the tiles or the roofing that we have to finish it up. And that's another example for wall. And if you try to keep this build-up in mind, you'll find a building that is working better, and which is going to be more durable as well, and it's going to last longer. And also the people who live into the building will actually have a better feeling inside it. So comfort is very important as well. And the permanent UV stability, that's another very important thing. We already talked about it. And you have a case scenario like this one that I'm showing in the picture, where a membrane can, when UV can pass through, for instance, the finish of your wall, and they can get in contact with a membrane. So in this case scenario, you have to come back to the technical sheet and choose a membrane which has a better resistance to UV, for example. And as I said before, also the breathe, having a ventilated facade, having air passing through is very good, because it enhances the also the way that vapor is taken away from the building. And this is just a very quick picture to show where to place the openings of this ventilated facade, because even if you have the air layer, if you do not have ventilation, it doesn't work the same way. So let's have a look at another stratigraphy, for example. When you have, for example, a timber frame building, it's more of an issue, because as you know, OSB is it stops the vapor. It's not breathable, and therefore I would suggest in this case scenario, for example, to use a vapor stop barrier on the inside, so that you don't have problems on the outside, for example. And if you have, for example, a CLT wall, it's common sense, and also the producer of CLT, they say that if you have a CLT with more than 3 layers, for example 5 layers, you don't need a membrane for the air tightness, because the CLT wall is already make sure that the air tightness is there. So let's talk about air and wind tightness now, which is just as important, because we just said that in our building we have air passing through, and of course we understood that inside the air we have the vapor, and so it can be dangerous for that reason as well. But inside, if we have air passing through our building, also the heat is going out, and as well the noise is coming in, because as you know, noise can pass very easily through air. So it's very important to have 2 main layers, and the first one is the air tightness layer, which is on the inside of our structure, and the second one is the wind tightness layer, which is important for the reasons previously discussed as well, and that's on the outside of the structure. So the air tightness layers, how can you have that air tightness? For example, the membranes are definitely a good way to make this air tightness layer, but we already said before that CLT can be airtight, and also the OSB is airtight, and of course, and as well, the use of plasterboard or a plastered finish of your wall can be airtight as well. And the air tightness, you can to achieve the wind tightness, you can use of course membranes as well, but you can as well plaster or CLT, so basically the same materials as before. And as you can see here, it's all about the joints, because once you placed the membrane in place, you have to make sure that you you fill all the gaps, basically using, for example, the tape that you're seeing in the picture. So how it is done. So this is, for instance, our very famous FlexiBand that you can see here in the image, and we're going to talk about how this is done. It has a release liner that you can use to open up the glue layer. Of course, it has an adhesive, and this in particular, it's a very, very strong one. It's well known to be a very strong one, and of course the support, which is the outer skin of our product, that the one that has the logo, for instance, on it. So we can use this different kind of tapes, and there are again a lot of tapes that you can choose from, and all of them have slightly different features, but all of them are doing the same thing. They are pretty much welding, let's say like that. They are connecting the membranes together, so that also you do not have gaps, for instance, and also they are used on every single gaps that you can have on your building, to close it out, so that you do not have air passing through. And again, the tape needs to be resistant, so it doesn't have to tear apart, and also the resistance to water is another very important thing. So there are a few tapes which can just be used on the inside, because they have more of a paper finish, and others that are the outer skin is done is more a plastic material, and they have a better resistance on the outside as well. So it's important to choose the right tape as well. So mechanical and temperature is very important. And to help you out in our technical sheet, we have as well this scheme that is showing you where you can use a membrane, on which materials, for example, you can use a membranes, and it's giving you a good idea for the installation. So as I said before, it's important to first of all to choose the right membrane. Second of all, you have to use it in the right way, otherwise it's not working in the right way. So let's have a look at some installation hints, for instance. So the connection to the ground is one of the most important things. One of the most important things in a timber building, especially because you have to protect the timber structure from the humidity that is always there when you have a connection to the ground. So first of all, it is very important to keep our timber structure away from the ground, and that is usually done with this concrete wall that you have on the bottom of your CLT wall, for example. That can be achieved in other ways, like for instance, that's more of something that you used in the past, not anymore now. You can use also a timber structural member on the bottom, or you can use innovative materials, like for example this Alustard, which is a product that Rothoblaas just designed, and it's available on the market. It's basically an extruded aluminum section that can actually keep apart your timber structure from the ground. And so that's the first thing, first of all. And second of all, you have to place the right membranes to prevent the water to get in contact with your timber, for instance, or your structure. So let's have a look now at these pictures here that we can see here. So first of all, it is very important to place a membrane to prevent the water to get in contact with our timber structure. And another very important thing is the product that you see down here. That's mainly for the airtightness. So it's basically stopping all the air from passing through. And I have some products right here, and I will show them to you right now. So as you can see here, this is mainly done of two little tubes that can be squashed. And so when you place your CLT on top here, this gets squashed, and they close all the little gaps that you might have. This one works pretty much the same way. So again, here you have this soft part, which is basically closing every single gap that you have, for example. And so you can see here a list of products, the Rothoblaas products that you can use for this reason. Another very important thing is the radon. Radon is a gas that sometimes it is inside the earth, so it can come out from the earth, and it can be bad for the human. Can be very dangerous for human. So it is better to place, when you have actually this gas coming from the earth, it is better to have a membrane that can actually stop it, so that you don't have the issue anymore. And let's have a look at how to place the membrane. Of course, it has to be placed on the bottom of your wall, and of course it has to be sealed very well, so that you don't have gaps where the radon can pass through. And that's for example an example when you have the the little concrete wall that we talked about before, you have to prevent there with an extra piece of the membrane. You have to enclose this one as well into the protection of the membrane, for example. Let's have a look at the windows of our buildings. Of course, it's easier to do a continuous wall, but as we know, windows are always the part of our building which has to be constructed really in the right way, because it's where you might have issues if you don't do things in the right way. The issues can be seen, for example, in this pictures done with a thermal camera, and you can see that there's air passing through, and those black things that you can see in the image is basically the colder air which is passing through. And again, we can have the same issues of condensation as well into our in this part of the window corners, for example. We can see here, for example, superficial condensation, and we can have interstitial condensation as well. So these are the places where we have to protect. And how do we protect them? There are always 3 levels of protections. There's the outside layer, which is the blue level in the picture, and it's basically protecting the window from the water coming from outside. We have the yellow level, which is basically in the middle, and it's really preventing the air and the cold air to get in, and as well the noise, because noise comes together with air all the time. And we have a red layer on the inside for the airtightness. So these are just examples of how you can achieve these 3 levels of protection. So, for example, on the outside, you have a membrane that is that covers completely your window, so that air and water can get through. Of course, this membrane has to be continuous with the other membranes in your building, so that you make sure continuity is there, and it is very important. The yellow layer can be done with foams. It is actually better not to cut out the foam like that, because this foam is has closed cells, and if you cut it out like that, you can open up the cells, and the airtightness is not just as good. So I would suggest to push it in with your fingers while it is just being placed. It's very easy to do, and you can use, for example, things like, for example, this soft materials here on the middle layer that can actually close every single gaps, just like we explained before. So these are already expanded, but they are very small before expanding, and they close every single gap. And the final level is the red level on the inside, and you see, for example, here that you have your membrane, which is continuous in this case scenario with a plaster finish of your wall, because plaster is airtight just as the membrane. So you make sure you have the continuity. These are the products that you can use with to achieve this for Windows. And just as a reminder, I want to tell you that you can find already these details onto our website, for instance. So if you want to have a look at them, they are free to download. And of course, another crucial part of our building is the roof opening. Works exactly in the same way. We have as well those details downloadable for free from our website. So we can continue. Let's talk about the first floor. The first floor, it is very important to close every single gap. For instance, here we see the 5 layers CLT, for example, so you don't need a membrane, so you just have to close out the gaps here with tape. Or in this other example here, you close down the gap of this beam into the structure, or you can use this xylophone is really mainly for noise rather than the air tightness, but it is slightly airtight as well. Or you can use products like this one, or like this one here in the picture. This is another list of the products that you can use, and again, an example that you can download again from our website. And the roof pitch, let's see how it works, and that's maybe the most important part of a building, because it's actually protecting our building from water, and which is very dangerous. Actually, water damage is one of the main damage in buildings, and especially for timber is very important to prevent it in the right way. So these are some examples of products that you can use for connections, and you can see here the Aladdin stripe, for example. This is very good for because it's preventing the noise to pass from the above level to below, but it's very good for air tightness as well. And I will show you right now the product so that you have a better idea of how it works. It's basically, it's done like that. It has these lines that can actually get compressed. When it's compressed, it becomes just a 3 millimeter layer, and it can be divided into two like that, so that you can actually place it on one side of the beam. If you had like a wide beam, you can place it on one side of the beam and on the other as well. And other very important products is, for example, that's just an example of how you place the membrane when you have cantilevering beams, for example, and how you close out every single gap. This is again a list of the products. And this is just a hint that I would like to give you. Just again, on the roof, you can use this inclined screws, so that you divide completely the structure from the finishing, and you're sure that you have a continuous layer of insulation. But of course, you would have a membrane here that you have to punch through to insert a screw, obviously. And so what's best for this case scenario? This is a very good product because it gives actually protection to the membrane. It is especially for nails and screws, and when the screw, for instance, is passing through, the product is really sealing every single gap, and so you're sure that you don't have air passing through. And that's again something that I would like to show you. On our website, you can find all of this information and a lot of interesting stuff to download that I just explained to you. So the last thing that I would like to talk about is the reaction to fire. Of course, on the technical sheet, you can see how the reaction to fire works, and we have these letters that we can see below here that are showing you what is the reaction to fire of a membrane, for example. And let's talk about monolithic and microporous again. And as you can see in the red box, a monolithic product has got a better reaction to fire than a microporous one. So as well as a lot of other characteristics here, a better durability, a better UV stability, and chemical stability as well. So of course, monolithic membranes, they cost a little bit more, but they are more sophisticated, and they work better for all these reasons here, especially now that attention to fire is always top grade in our buildings, especially in the public buildings. And here we can see, for example, the reaction to fire that our membranes have, and we are gonna have a look at what this letter means in particular. So what does it mean, B, S1, D, 0, or E or F? We're gonna see it in the next slide. So the European standard EN 13501, it's telling us what the reaction to fire is. And the reaction to fire is the response of a product in contributing by its own decomposition to a fire. And as you can see down here, it is classified according to tests in classes. And these classes are A1 or 2, B, C, D, E, or F. And of course, all these materials, you can see all the list of materials down here. And basically, A2 and A1 materials are non-combustible materials, so they cannot, they don't have reaction to fire at all. And the membranes are, most of them are combustible materials, but they are usually not very combustible, and because they are, some of them are BS1, and so that means that it's not very combustible. And let's have a look at what the other letter means. What about the S? S stands for smoke emission level, and it's divided into 3 classes. And the class 1, so S1 is stands for the speed of emission of an emission of smoke, which is very weak. And class number 3 is a very high emission of smoke, for example. So, for example, to come back to our membranes, the ones to come back, and let's go back to the slide. For example, the Traspir Evo 90, which is a monolithic product, it is combustible, yeah, but it's not very much combustible, like you can see here. S1 means smoke 1, so the first it doesn't produce that much smoke. And let's have a look at what D stands for. D is the production of flaming droplet. So basically, when a membrane, for example, is burning, it could produce some flaming droplets which are falling down and which can be dangerous for the rest of the building as well. And so D0, that means that there is no production of this flaming droplets, for example. And that's very important, of course, for a membrane. And like that, my presentation is over, and I would like to show you a final video so that you can see really how the reaction to fire in real life, in real terms, how it works. And so I'll leave you guys with this small video, and I hope you liked the presentation, and I hope to see you again in the next lesson. Thank you very much.
and thank you for staying with us until the end. It was really a rich presentation, I believe. We have a number of good questions into the Q&A. We have Milos Slavic, which is the country manager. Sorry if I'm not referring to you exactly with your title, but basically this is what it is, the contact person in Australia and New Zealand.
Yes, hello everyone. Thank you for coming and joining us today.
And yes, it's a rich presentation, which provided us with a number of good questions. So let's run through them quickly. The one from Graham Barron about the influence of climate is the most voted one. So I will start with this. Can you see it, Milos?
No. Can you repeat?
Open up the Q&A. You should
yes.
read it. But anyway, I will read it. The building science seems to assume a northern climate, where the temperature is typically colder outside than in the building. However, in a hot Australian climate, the temperature outside, temperature outside is typically hotter. This changes the direction of the vapor drive and means that the vapor barrier needs to be placed on the opposite side of the insulation. The vapor barrier should always be on the warm side of the insulation. I'm not a big expert in building physics. What I know from my past experiences is that, first of all, the climate is not always hot. Just in few areas in Australia, it is hot throughout the year. In most climates, it varies between winter and summer, and it varies significantly between day and night. Keep in mind also this. Normally, the vapor is driven by the vapor gradient, not by the temperature gradient. And typically, the inside of a house has a bigger vapor amount, and therefore the gradient goes from inside out. But I may be wrong or may be limited into some cases. There are specialists into this. Rothoblaas has their own specialist, and Matteo is one. So ask them the question.
I agree. Look, I mean, in Australia, because being such a vast and huge country and continent, look, there is so much difference. But looking at Melbourne climate or ACT climate, we are pretty much like the European one. So it really depends. That's why this lesson or this webinar should have been more an overview of. It is very important to pay attention to the drafting of the house. And then when these questions arise, we are here to help. We are here to guide you through this process. So just simply really for anyone who is interested having a catalog or having more information, please contact us. We are here to give you this advice.
And we will provide support. It's project specific. Remember this.
Project specific.
Very project specific. A second interesting question, apart from the slides appear blurry, which is not in my computer, and we will probably be able, Milos, I think, to provide the link to the original video.
Yes, yes.
Okay, right. So the other question from Peter Chisholm is, how do you fix the membrane or barriers to the structure without puncturing the product and causing points of weakness? Would you answer that?
Yeah, look, I mean, you cannot really avoid puncturing the product. It is how you pay attention to installing it. We do have certain products which are nail plasters or plaster bends, which when you puncture through that, it closes the cells. So again, helps you to avoid these puncturations. If there is a slightly bigger hole, you just simply tape over it. And this is the detail you have to pay attention to. So no problem with little small holes.
Yeah, perfect. You can tape them over. If really
absolutely.
Another popular question from Hamish George is that noting that the monolithic fields use a chemical reaction to transpire, is there a lifespan for the product when the chemical is no longer active?
Well, that's a good technical question. Look, I assume that these products would last the life of the building. There is not really a specific years. What do we say? So I can really answer this one by asking our headquarters, so I can get back to you on this one. But I would assume that it's 20, 30 years.
Yeah, and Amish asked another popular question, a relevant question, which I believe has been answered by one of your colleagues into the chat. But anyway, what is the formal relationship between EN standards and Australian or New Zealand standards required under the NCC? I understand you have tests according to the Australian standards as well.
Look, the Australian standards, they don't really exist on membranes. So what are we referring to has to be really looked at. The only one which is relevant, it's the flammability index, and in European norms, it's BS1D0. It's classified, and in Australia, we are calling it flammability index 1 to 5. And all our membranes classified BS1D0, they have been retested to Australian standards or to this particular test of flammability index, and that's the only one. There is really no specific Australian code for membranes.
While for the other performances, yeah, the standard may differ a little bit in terms of how the test is being run, but they are quite comparable. So
I agree.
Comparison
I agree.
is possible. It's not difficult.
Yes. Most of the products, when you look at how they are produced, even knowing the Australian made, are not made within our country, so they are all imported according to my knowledge.
Okay, so scrolling down. Gary Windy says, I am unsure if this is relevant to Australian construction. We are told to use vapor barriers, not solid barriers. And solid barriers create sweaty building. Again, it's a question of design, how you use the barriers, okay? Yeah, that's another question from John Skerr. He says, why is the internal side of a wall made impermeable when this will cause superficial condensation on the inside? I think in most Australia, at least, the condensation on the inside is more of an issue than the heat loss. Though a standard timber frame plasterboard wall with a R2.5 fiberglass insulation and breathable membrane on the outside and the wall lining. Yeah, this is correct, and it's a specific case, I believe.
And it is a specific case. You don't always require to have a vapor stop on the inside. So you could be fine really just doing the breathable membrane from the outside.
Because now the questions are moving up as people are voting them.
Yeah. That's right.
So I went back to that one. There's an interesting question that says, is a water column test only performed in a laboratory? Is there an on-site test? I've never heard about it. Milos, have you?
No.
On-site test. Yeah, to check, to do quality control. But yeah, there is an intensive quality control in the factories, I believe.
Yeah, correct. And when you saw one of the videos presented today, you can simply cut out of a little piece of the membrane, make a little bowl out of it, pour water inside, so we can really perform a test prior very simply.
It's empirical, but it tells the story, right? I remember years and years ago when the first breathable membrane appeared on the market, I'm talking more than 20 years ago, we were used to put them on our mouth and try to breathe through to make sure that they were breathing, and they were. This is interesting. From Alwyn Williams, what happens when the warm side of the building changes throughout the day? So the sun moves across the sky, okay, and from east to west, and therefore, yeah, there is a change. And you need to consider that in your design. Typically, so Milos, if you want to answer.
Look, we also have variable membranes, so they act as a barriers and a breathable membranes in the same time. But this doesn't really happen during the day. The properties of such a membrane really takes from a season to season. So it really depends. Again, it's a design question. So if I see on the drawings, I can help.
Yeah, I agree. And I mean, it may be relevant or it may not. I think shorter time periods are more relevant in terms of shading, for instance. Creating the right shading in the right moment will be most effective. But why not? Looking at some details and specific cases may be interesting. Yeah? So Alvin, please do it. Send us your drawings and we discuss it together.
We provide, I want to just highlight that we provide as a Rothoblaas this service free of charge. So when there is a project going with us, you have access, you can tap into, you know, the knowledge we have across the globe. So you can tap into a knowledge of, let's say, 400 salespersons around the globe. And we are speaking really different climates, different zones. So this is all what you get. And we are happy to do it with you and give you this this knowledge.
Scrolling down and I see a lot of many other interesting questions. So
I can answer them.
Yeah, I believe.
If you send them Paolo to me, you know, I can answer the questions.
Yeah, and I will say
I will respond.
It's 12:15. So although I see 360 of you still online, and that's a great thing to have, I think we need to close. We will send to Milos or to Matteo through Milos the whole set of questions, and I believe they will be able to answer in a couple of weeks, probably through us, like we did in the past with other presenters. So I really thank you very, very much.
Thank you everyone for coming. And
I want to remind you that we have a beautiful series of videos, short videos, which are also from in our website and I think also on YouTube, describing how it's made for different products, for different techniques. So please, you're welcome to see these videos as well. And I shall see you next week for our next webinar. Have a great day and thanks again for joining us.